what we know is that, so we've gone through the first two approaches. If we have bits, digital data, if I want to send digital signals, then I simply map the bits into one of the different pulses. That is, bit 0, high voltage, bit 1, low voltage. But it can be more complex than that, and we saw the different encoding schemes: non-return to 0, bipolar AMI, Manchester, and there are others. So they are encoding schemes if we have digital data and we need to transmit digital signals. If we have digital data, zeros and ones, but we need to transmit analog signals, then what we do is we vary our simple sinusoid signal based on one of those three variables: amplitude, frequency, and phase. If you remember back to our simple sinusoid equation, there are the three parameters that we can change. If we want to transmit a bit 0, use a low amplitude of our sine wave. If I want to transmit bit 1, use a high amplitude of the sine wave. And similar with frequency and phase. So they were amplitude shift keying, phase shift keying, and frequency shift keying. And in fact, they can be combined together. That's with digital data. And we're going to start to look at, okay, what happens now if we have analog data? And we want to transmit digital signals and eventually analog signals. To illustrate the next two, and also some of the ones that we've gone through, we'll use an example of this audio system in the room. And I've tried to illustrate it on the board in this diagram. We have me talking using the microphone, and the microphone in fact is cabled, is wired down to the wireless transmitter in my pocket, and that wireless transmitter sends to the receiver, which is on the desk here, which has the two antennas on it, and that receiver is in fact cabled into the amplifier down in the cabinet, in the cupboard there. The amplifier increases the strength of the signal, sends it up through the cables to the speakers in the two corners. So here's one of the speakers, and the speakers produce the sound waves that come to you, the listener, and you receive that signal at your ears. We'll see another case on this side in a moment, but let's focus on the basics first. So what's the data that we are communicating in this place? What type of data? Analog or digital? Sound is analog or digital? Analog. It's analog data. The sound waves is analog data. So that's the data that's coming out from the source here. Analog data as sound waves, as acoustic signals essentially come out. And so we think of analog data reaching the microphone. What a microphone does is converts these sound waves into electrical signals and sends electrical signals down through the cable to the transmitter in my pocket. So let's say we start with analog data, and of course you as the listener need to receive that analog data, and your ears will receive the sound waves. We'll look at the different, or at selected different links in this system and see what type of signals are we sending and how do we convert between them. We'll see in this example there are different, I think we have all four cases covered. Yeah, all four cases covered, so we'll go through that. First, what we'll do is the microphone receives the sound waves and converts them just into an electrical analog signal and sends that signal down the wire to the transmitter. So we can say in this part we have an analog signal. From the microphone to the wireless transmitter. What range of frequencies is the analog data? My voice, approximately? What's the maximum frequency normally of voice? Voice ranges in what frequencies? You don't know? 20 hertz to 20 kilohertz. Okay, that's maybe a little bit larger, but yeah, usually in a matter of several kilohertz, 3, 4 kilohertz. Yep, but up to 20 kilohertz possible. So that's the analog data. What does the analog data look like? And eventually what happens is the voice, which is acoustic signals, is received by the microphone, converted into electrical signals. And in fact, the way that the microphone works is it simply takes the input sound waves and transmits them as analog signals. There's no change of the frequencies. Let's look at what is the original input data, and also what is that first signal sent from microphone to the wireless transmitter. Of course, I record these lectures, so this is the recording from yesterday, or a portion of it. It's just a software that shows the recorded voice, the analog data. So look at this blue part. You've seen similar types of plots in other software, in audio software, for example. So it's showing as a function of time, so time going from 0 up to 5 minutes. It's only a portion of the recording. And the signal strength changing over time. So this is a plot of time and our voice intensity changing over time. You see it's something like this, and then there's moments of silence and so on. And of course we can zoom in and see the details, but so we can see the moments of silence. So over this 2 seconds, I'm not talking, and then something's being said. We see the signal strength or the voice strength changing over time. There may be some background noise as well measured here. So this is our analog data shown as a function of time. In fact, what our microphone does is takes this and essentially transmits as is, as a signal to the wireless transmitter. So this analog signal going from the microphone to the wireless transmitter looks like this as well. If we drew a plot of that analog signal, it's varying over time, representing the acoustic sound, or the acoustic signal. Of course, we know that we can look at a signal from the perspective of, as a function of time, like shown here, but we also know any signal is made up of different frequency components. It has some spectrum and some bandwidth. So in this software, we can also analyze which frequency components are contained in this signal, and this is a plot of what it is. What it's showing along this axis is the frequency. So it's a plot like this. Frequency and the peak amplitude. So it's our signal in the frequency domain. The frequencies here we see starting from 1 hertz, 1000 hertz, 3000 hertz, up to about 20 kilohertz. And the peak signal strength, it's measured in decibels here. The important point is to look at where is it strongest. Which frequency components are the strongest in this signal? Now the plot itself may be a little bit misleading to you initially, because with it, as it's in decibels, this is really a logarithmic scale. That is minus 48 decibels. This is the highest signal strength, the peak up here. Minus 51 is in fact twice as weak as minus 48. 3 dB is a factor of about 2 in the absolute measurements. So in fact, this signal compared to here, although it doesn't look like much compared to the rest, this is a factor of 16 times weaker. That is, the signal at this frequency component, around 2 kilohertz, is 16 times smaller than at about, 500 hertz. So this is a plot of our signal. Looks something like this. If I drew it in a linear scale, the peak is concentrated in this range of the spectrum. Then it gets much weaker. Even though it looks like it's quite high here, it's very, very small in a linear scale, because this is a decibels or a logarithmic scale. So the point is that most of the signal strength is concentrated in this area of around several hertz to 3,000 hertz. And that's the frequencies that voice are mainly concentrated in. We see a peak here, which is quite high, of what, around 8,000 hertz. Maybe that's just some noise that was measured, maybe some feedback or some interruption from in my laptop when I recorded that. So the voice frequencies mainly in this range. The rest are just other frequencies from the air conditioner, from people speaking, from noise in the communication system, which, although they look high in this plot, if you plot them linear, then this is very high. These are very, very, very weak. So it looks something like this. Of course, there are frequencies or components with frequencies in these up to 20 kilohertz. But approximately the bandwidth, most of the energy is contained in this area. Maybe in this area, most of the energy up to about 3 kilohertz. So the bandwidth of that signal is about 3 kilohertz, the practical bandwidth. That is, if we transmitted only this 3 kilohertz, we would contain most of the information. If we omitted all of this, because in fact most of this is very weak, we'd still get the same, or approximately the same data received. So that's an example of our voice plotted in the frequency domain, and the previous one with the voice plotted in the time domain. So, coming back to our communication system, I talk, the microphone simply converts the acoustic signals, the sound waves, into electrical signals and sends those electrical signals as is, that is, looking like in these plots, to the wireless transmitter. So from the microphone to the wireless transmitter, analog signals. Bandwidth, most of the energy is in around 3 kilohertz, maximum of about 20 kilohertz. But in fact, most of this is quite weak in terms of signal strength. So that's going from the microphone to the wireless transmitter, an analog signal containing the analog data. The wireless transmitter in my pocket transmits also analog signals to the wireless receiver here. So this was a wired medium, the first one. Here, we also have an analog signal. The frequency components of the input of this original analog signal was, what, around 0 to, let's say, all right, from our plot, 20 kilohertz. That is, from this plot, from 0 up to 20 kilohertz. But in fact, most of it finishes up at about 3 kilohertz. That's the frequency components, or the spectrum of this analog signal. It comes to the wireless transmitter. What this does, one option would be to transmit as is, components ranging from 0 to 20 kilohertz to the wireless receiver. But in fact, what it does, to be practical, to transmit over a reasonable distance, transmit within a portion of the spectrum that is allocated for wireless microphones, it actually transmits, and I checked, at around a frequency of around 670 megahertz. So our input signal was from 0 to 20 kilohertz. Depending on the particular channel of my wireless transmitter and receiver, it has a bandwidth, of about 200 kilohertz. Let's check this. The analog signal sent from the wireless transmitter to the receiver is approximately ranging from 670 megahertz to 670.2 megahertz. The 0 to 0.2 means there's a bandwidth of 0.2 megahertz, which is 200 kilohertz. That is, this wireless transmitter transmits a signal with a bandwidth of 200 kilohertz at a frequency of around 670 megahertz. My voice and the original signal had a bandwidth of 20 kilohertz at a frequency, well, from 0 up to 20 kilohertz, maybe centered about on 10 kilohertz. So when we talk about a signal, there's two parts of it: the frequency, or usually the center frequency, and the bandwidth, the range of frequencies. Our input signal had a range of frequencies from 0 to 20 kilohertz, let's say at a center frequency of 10 kilohertz. The signal sent from our wireless transmitter to the receiver has a bandwidth of 200 kilohertz from 670 to 670.2 megahertz. So in fact, the center frequency is around 670 megahertz. 670 million hertz, as opposed to 10,000 hertz. So, in fact, what my wireless transmitter does is it shifts the input signal and the original voice data to a different frequency, and it, in fact, does modulation. Let's come back to our slides. The last thing that we're going to go through in this topic is how do we take analog data, such as my voice, and transmit as analog signals, such as the signal from microphone to the wireless transmitter. Well, how do we do that? Well, it's very simple. We just take the input analog voice and transmit as is to the wireless transmitter. But in some cases, we want to shift the frequency of that input analog data. My voice has frequency components in this range, my wireless transmitter in a different range. Why? Because at this frequency, 670 megahertz, we can transmit over different distances. The antennas we need to transmit are much smaller. Generally, the lower the frequency, the larger the antenna. If I want to transmit low frequency signals, I need a very big antenna. I cannot fit a very big antenna in my pocket. So by shifting up to 670 megahertz, I can have a small antenna and transmit to the wireless receiver. It can pass through obstacles differently. So this is the portion of the spectrum allocated in Thailand to wireless microphones. I'm allowed to transmit at this frequency. In fact, on the back of this device, it has some approval by the National Telecommunications Commission, some class device which says it's allowed to be used in Thailand at this frequency. So to transmit analog data as analog signals, one thing we often do is shift the analog data from one low frequency up to a higher frequency, and we perform some modulation. We'll go through how that is performed if we get time at the end. So an analog signal comes to my wireless receiver here, and that sends down to the amplifier, and in fact it converts back to the original analog signal from the microphone, back to the normal 0 to 20 kilohertz. Sends it to the amplifier in the cupboard. The amplifier increases the amplitude of that signal, so it makes it stronger. Sends it up to the speakers. The speakers do the opposite of the microphone. The speakers take the input electrical but still analog signal. We've still got analog here and analog here. Takes the input analog signal and converts it, and it's an electrical signal, converts it to an acoustic signal, sound waves, and sends them to your ears, and you hear the voice. So this is an example of analog data being sent as analog signals all the way through to you. We'll look at how the conversion can happen in this part of the topic. The other thing I do is connecting the amplifier to my laptop to record the lectures. So there's a cable from the amplifier. It sends an analog signal to my laptop. My laptop takes this signal coming in, records it, and saves it as a file. And my laptop is saving it as a binary file, as digital data. So my laptop takes the input analog signal and converts it to digital. This conversion from analog to digital is what we're about to cover in a moment. Now, what happens if I want to send this audio that I'm recording from the laptop and send the file, or even stream the file, to some PC, maybe in another room, via the LAN cable? I plug a LAN cable into my laptop, it plugs into the wall here, and it goes to the PC in my office. And someone's sitting in my office with the speakers on, and they can listen to my recording. In such a setup, so this connection from the laptop to my PC in the office where we're sending to, it's an Ethernet LAN connection. And Ethernet, or wired LANs, use digital signals. And an example, so in fact my computer has digital data. Analog signals come in, it converts the analog input signals to digital data. And then if I want to send that file across the Ethernet, I use digital signals. So I'm in fact sending digital data as digital signals. We covered that in the first part of the lecture yesterday. We could use non-return to zero encoding. Ethernet, in fact, uses Manchester encoding. Remember, if you look back at the slides, you'll see one of those ways of encoding bits to digital signals is using Manchester encoding. That's encoded, sent to the PC. The PC receives the digital data, converts the digital data back to analog, and it's played on the speakers on the computer. So it sends, if I've got speakers attached to the PC, then it sends an analog electrical signal to the speakers. The speakers generate acoustic signals, that is, sound waves to the person listening. So here's an example where we convert analog signals to digital data, and using our wired LAN, we're transmitting digital data as digital signals. Third case, so this was sending to the speakers up here. This was sending via the wired LAN to some computer. I don't want to use the wired LAN, I want to use my wireless LAN. Don't plug a cable in, send to the access point. There's one out in the corridor. Send wirelessly from my laptop to the access point. And wireless LAN uses analog signals. So here's my laptop. Here's the access point, WLAN access point out in the corridor. It has analog signals. So my laptop has digital data. The digital representation of the audio. We had analog in, it converted from analog to digital. So it has digital data. If I want to send that or stream that to another computer wirelessly, I send that digital data as analog signals. That's what we covered at the end yesterday. If we have digital data, we can use things like phase shift keying or amplitude shift keying. When I have a bit 0, have a sine wave with one amplitude, a bit 1, a sine wave with another amplitude. Shift the amplitude depending upon the bits. So using the wireless LAN is an example of sending digital data as analog signals. And then it's received by the wireless LAN access point, and that's an access point. And then that sends digital signals to the PC and someone can listen to it in the same as what we sent here. So, in this example scenario, we've got our digital data sent as digital signals here, using Manchester encoding, which we covered yesterday. If we use wireless LAN, we had digital data, that is the audio, but stored in a digital form on my computer, sent as analog signals over the wireless LAN link, using amplitude shift keying, frequency shift keying, phase shift keying. In fact, wireless LAN uses a combination of phase and amplitude shift keying. That's an example of those techniques. Sending from the microphone to the wireless transmitter, and the wireless transmitter to the wireless receiver on the desk is taking analog data and sending analog signals. We'll cover that last. And at this point, we had analog signals coming in, and we converted them to digital data to be sent across the Ethernet or the wireless LAN. How do we convert the analog input to a digital form? That's what we'll cover now. And then once we've covered that, we'll see how it works in our example scenario. So what we do, if we have analog data, such as my voice, and we want to transmit as digital signals, we convert the analog data into digital data. And then transmit that digital data using one of our existing techniques for sending digital signals, like non-return to zero or Manchester. So the important part, how do we convert analog data to digital data? How do I convert the recording or the voice, which is analog data, into something that my computer can save, which is digital data? In some systems, we may even convert the analog data to digital data, then send that digital data as an analog signal, like over the wireless LAN. I have analog coming in to my laptop. I convert it to digital data, save it as a digital file, convert it back and transmit analog signals. Often saving and using digital data is more efficient and can lead to more benefits than having it in its analog form. The key point here, how do we convert the analog data into digital data, or digitize the analog data? We use a codec. A codec is a coder and a decoder that does the conversion. It takes the analog, converts to digital. The decoder recovers the digital data from the analog data. There are two techniques. We'll cover the first one and maybe the most basic one, pulse code modulation. The lecture notes also have an example of delta modulation. Let's look at PCM. And think, if we go back to our example briefly, this is our input analog data. Imagine this is our input analog data. This is just a recording of my voice from the lecture yesterday. Over time, the signal strength changing. So that's our input. We want to convert that to binary, to digital data. How can we do that? Well, pulse code modulation, what we do is we have an input analog information, continuous in time, continuous in amplitude, so continuously varying. We have a sampler. So it's called a pulse amplitude modulation PAM sampler. What it does is it takes every sample point, it takes a measurement of the signal strength. It takes a sample. And that sample is matched to a particular level. Because we have a continuously varying amplitude, with digital data we need discrete levels. So we take our input magnitude and divide into 2 to the power of n different levels. We'll see an illustration of this, and the levels are referred to as code numbers. We sample the input analog signal or data every TS seconds. TS, S the sample time, the sample period of TS. If the sample period is 1 millisecond, every 1 millisecond I record the value of the input and match that to one of our discrete code numbers. The resulting value is called the PAM value, pulse amplitude modulation value. We get a code number, a binary value, or we get a code number in decimal, and then we convert it into an n-bit binary value, which is called our PCM code. Let's see the example to illustrate that. So here's a portion of our input analog data or signal, shown in the plot here. So that's a portion of, say, a portion of the voice being recorded, like we saw on the previous, on that real example, just one portion, small time slice of the recorded input analog. What we do, we look at what's the minimum amplitude, the minimum possible amplitude, and the maximum possible amplitude, and we divide that space into some discrete values or discrete levels. In this example, we divided it into 16 different levels. It can be more than 16, but just for this example, into 16 different levels. So the first level here, between these two lines, the second level, the third, and so on. 16 different levels. This is time increasing, and this is the signal strength. Every sample period, we measure the strength of this input. So, at the first point here, time 0, when we start, we measure the strength, and we measure it to be here, which is 1.1. Okay? What are the units? It's just a value of the signal strength. It's volts, some decibel value, doesn't matter. 1.1 is the magnitude of the input signal here. So that's referred to as our PAM value, 1.1. We map that to one of our code numbers listed here. So 1.1 is in this level. between here and here, so in these two, within these two black lines or solid lines. So we map that to code level 1. This is the first level, the second level, but we start at 0. So this is level 0, level 1, level 2, level 3, level 15. There are 16 different levels. So this sample with a PAM value of 1.1 gets a code number of 1. That's the decimal code value. We simply convert that to binary. And in this case, 4-bit binary, because with 16 possible levels, we need 4 bits to represent any of those levels. 1 in binary is a 4-bit binary value. What is the decimal value 1 as a 4-bit binary number? Quick. You're on the right track. Try. 4 bits. 0, 0, 0, 1. Okay. 4-bit number. Why? Because with 16 levels, we will need 4 bits to represent any of those 16 values. So we say for this sample, the PCM code is 0001. The sample period TS is this duration. So at this point, we do it again. Measure the value. It's 9.2 at this point. That corresponds to this level. And that corresponds to code number 9, the 9th level. If we start at 0, this is the 9th level. And convert that to binary. A 4-bit value is 1001. And we continue doing that. So we take samples at a regular period, a regular interval. We measure the value of our input signal and convert it to a binary value. So over time, this is our input analog. This is our output digital data, this sequence of bits, 001, 0001, 1001, and so on. So that's how we convert our input analog data into our output digital data. And we continue to do that as we get the input analog. Two design issues arise. How often should we sample? Here, all right, we take this sample. What happens if we sample at a more frequent rate? And how many levels should we have? Here we have 16. What happens if we had 32 or 1024 or 2 levels? So two parameters we have is what's the sampling rate? How many levels do we break the magnitude into? We'll see the impact of them. Now, what happens at the receiver? We sample the input analog. We get the digital data. So that's the, say, the analog to digital conversion. My computer sends the digital data. The receiving computer converts it back to analog and plays it on the speakers. Let's look at what that resulting analog would look like at the receiver in this case. This is a plot of the input analog. Let's plot the output analog at the receiver. A function of the signal strength against time. So we have our sample periods. How many? And we have our signal strength, which is broken into 16 different levels. So let's try that. Eight. We have our input analog data, convert it to digital data, transmit those bits. So the receiver receives those bits. So the first bits that we created was 0001 from the first sample. Transmit those bits, and let's say we receive those bits, 0001. So when we receive those bits, we convert them back to the decimal value, which is 1. And that indicates what the signal strength should be at the output. What's happening at the receiver is we receive the digital data. We need to play back some audio. So what we do is we generate some output, and that's sent to the speakers. An output at a particular level, and the next sample period will change the output according to the bits that we receive. So value 1 let's produce an output at this level. If we have 0, 1 up to 15 there, we produce at the receiver an output at this level and hold it at that level for the sample period. Then we receive more bits. The next sequence of bits is 1001 because what the transmitter did, took a sample, converted to 1001, transmits those 4 bits, we receive them in decimal, that's 9. When we receive the bits for this sample period, we produce an output at this level. Then we receive 1111. One oh one oh, which is 10. Five. Two and 2. That's our output analog signal at the receiver. This is the input analog. This is the output analog. Well, it doesn't look very analog, but that's all we can generate because the only information we have are these numbers, 1, 9, 15, 10, 5, 2 and 2. That's all the information the receiver has. So the basic way to deal with that is that, okay, produce an output, say a voltage level at one level, at the level 1 for the sample period. Then produce the output at level 9. And then at level 15, 10, 5, 2 and 2. Note that what I did is I drew them between 1 and 2. So if we had 1, I drew between the mark here 1 and 2. That is, this is level 0. This is level 1, or the code number 1. And I simply produced an output in the middle of that level. That is at this dashed line. If we could map this diagram to here, I drew the output where the dashed lines were. If I had 1, I drew it here. 9 here, 15, and so on. Is it the same? Or no? The received analog data or signal is different from the transmitted. Does it look the same? Similar? Who thinks it looks similar? Does it look similar? The received signal, is it similar to the transmitted signal? Yes. How would you make it more similar? What would you change to make it so that what we generated here looked more like this? The receiver is on the other side of the world. They cannot just draw a line. All they've received is the digital data. How will we make it similar at the receiver? Increase the sample rate. I will not draw it, but try and imagine. Okay, we sampled at this point, this point. If we sampled more often, here, in the middle, here, here, then the first value would be 1. The second value would be whatever this is 3 point something, so 3. We would produce an output which would be 1, and then 3. Then we'd sample 9. And then we sample in the middle here, so we're sampling more often, and we get a value of 14. And then 15. And so on. We'd get a more accurate representation of what the input was by sampling more often. Increase the sample rate can give us a more accurate reproduction of the analog at the output, at the receiver. The other way to see that, what happens if you reduce the sample rate? Here we had 1, 2, 3, 4, 5, 6, 7 samples. Let's say we had 2 samples. 1 here and 1 here. Let's draw our output. If we had just 2 samples. If we reduce the sample rate, the first sample would be 1, and let's say the next one is 5. So we draw the red line would be our output if we had a sample rate with just 2 samples in this period. That is, decrease the sample rate, and the accuracy of the reproduction at the receiver is much less than what we previously had. This red line doesn't look much like this. Increasing the sampling rate increases the accuracy at the receiver. What else can we do? There's something else we can do. How are you going to make your reproduction of the audio at the receiver better? We can increase the sample rate. What else can we change in this case? Sample more often and increase the code number, that is, increase the number of levels. In this case, we had 16 possible values. What if we decrease and go to almost the worst case and have 2 possible values? This would be a sample if we broke this area or this space into 2 areas, here and here, 0, 1. The sample would be 0, 1, 1, 1, 0, 0, 0. We'd reproduce, and it wouldn't look as accurate as the original blue line. Increase the number of levels increases our accuracy of the reproduction at the receiver. Increasing the sampling rate increases the accuracy of the reproduction. Remember, this is a reproduction of audio. For example, I talk, computer converts it to digital, sends it, and that's reproduced into analog acoustic waves at the receiver, at the speakers. If the reproduction is accurate, then it will be very close to what I said. If it's inaccurate, low sampling rate, low number of levels, then it will be much harder to understand what was said at the receiver. So for accuracy, we want to increase the sampling rate, increase the number of levels. What sampling rate should we use? Our friend Nyquist, who gave us some relationship between bandwidth and data rate, worked on also what's related to that, the sampling theorem. And the sampling theorem says if we have a signal, our input analog signal, if we sample it at a rate or at regular intervals such that the rate is twice the highest signal frequency. Remember, our signal has frequency components. If the highest component is 20 kilohertz, if we sample it more than twice of that, say at 40 kilohertz, then at the receiver we can reproduce the exact signal. So it gives us a guide of what's the best or what's the ideal sampling rate. For example, voice normally has frequencies ranging from 0 to 4,000 hertz. So the maximum frequency component is 4,000 hertz. If we sample it twice of that, so 4,000 hertz is 4,000 per second, double that, 8,000 samples per second, that should be a sufficient sampling rate to reproduce the analog voice at the receiver, to give us perfect reproduction. So that gives us a relationship between the frequency of the signal and the sampling rate that should be used. But in fact, in practice, what we do is we have some digitization. We digitize the values. We don't have continuous samples. So in fact, the fact that we have code numbers means we do not get perfect reproduction, but we can get close. With voice, if we sample at 8,000 samples per second, and if we have 7-bit coding, that is 128 levels, we can get very good reproduction at the receiver. Hard to notice the difference between listening to the person in real life compared to receiving the digital form of the audio. So there's two factors, sample rate and number of levels. Sample rate, or the optimal sample rate, is 2 times the highest frequency component of the input signal. The optimal number of levels is not easy to determine. It's based on quality at the receiver. As an example, 128 levels is sufficient for voice. Music, for example, we may have a different number of levels if we want higher quality at the receiver. What's the problem of increasing the sampling rate? What's the problem? Increase the sample rate, what is the negative impact of that? Anyone have an idea? Not easy. Increase the sampling rate, we're going to increase the number of bits that we have to send. A lot of data. Let's say our sample interval was 1 millisecond in this example. If we take a sample every 1 millisecond, the sampling rate in this case, if we take a sample every 1 millisecond, is 1,000 samples per second. One millisecond, convert into the digital value, the binary value. Go back to our... Take a sample, 1 millisecond later, take another sample, convert to binary. 1 millisecond, take another sample, convert to binary. Send that binary from the transmitter to the receiver. With 1,000 samples per second, every sample is 4 bits. In our example, one sample was represented by 4 bits. Therefore, we're generating 4,000 bits per second. 1,000 samples per second, 4 bits per sample, 4,000 bits per second. So to send this analog data, we need to transmit at 4,000 bits per second. Let's increase the sampling rate. Let's say we sample at twice the rate. Sampling rate. Instead of 1,000 samples per second, let's say we sample twice as fast. We said increase the sampling rate, increase the accuracy at the receiver. Let's increase it to 2,000 samples per second. Still, 4 bits per sample, 2,000 samples per second. We need to send 8,000 bits per second. Let's compare the two. The first case, with a low sampling rate, to deliver that to the other side, we need to transmit at 4,000 bits per second. If I have a link that supports 1 million bits per second, then to send this voice, I need to send 4,000 bits per second. 4,000 out of the 1 million is to use to send this voice. If I increase the sampling rate, I have to send faster, 8,000 bits per second. That is, I use more of the link to send the same voice if I have a higher sampling rate. I use more capacity if I increase the sampling rate. That's a negative or a disadvantage. The higher the sampling rate, the more capacity required to deliver that to the other side. The advantage, the higher the sampling rate, the better the accuracy of the reproduction at the receiver. So there's a trade-off there. The same is applied for the number of levels. Increase the number of levels from 16 to 32. Instead of 4 bits, it will be 5 bits. Instead of 4 bits per sample, 5 bits per sample. 5,000 bits per second. Increasing the number of levels, increasing the sampling rate increases the accuracy, but also increases the data rate required, which is a negative. Let's return to our example from my recording of the voice. To illustrate that for a real case. So this is a recording of my voice from part of the lecture yesterday. So my computer has the analog input. It samples that analog input and it stores on my laptop digital representations of that analog using PCM. So let's do a calculation and see, for example, how large is the file to store this analog data. It's about 5 minutes in duration of the audio. So it goes from 0 up to 5 minutes. By default, my computer was configured to sample at, you cannot quite see it, 44,100 hertz. That's the sampling rate. So the analog data is coming in, is taking a sample at a rate of 44,100 times per second. It says here there's a sampling of 32 bits, but if I save it as a file, I can specify the number of levels to save it as. A common number of levels, sampling rate, is 16-bit encoding. With 16 bits, we have 2 to the power of 16 different levels. In our previous example, we had just 16 levels. Here we have 2 to the power of 16 levels. 16 million different levels. So take a sample of the input audio, match it to one of these 16 million possible levels. Short time later, take a sample of the input audio and we get the binary output. That's what my laptop does. As the analog comes in, it gets the digital data as out. How big is the file if we want to save this? Okay, it's 5 minutes, or a little bit longer than 5 minutes. 5 minutes is 300 seconds. So I want to save this, which takes 300 seconds of voice, sampled at 41 kilohertz, 16-bit encoding. How many bits do I need? Well, for every second, I have 44,000 samples, 44,100. 44,100 hertz means 44,100 samples per second. Hertz is per second. So every second, 44,100 samples. Every sample is represented by a 16-bit number. So in fact, every sample is 16 bits. Every second, we have 44,100 times 16 bits for 300 seconds, for 5 minutes of the audio. Let's calculate. $44,100, 16 bits, 300 seconds. That's the number of bits. 211 million bits. Divide by 8 to convert to bytes. Might be easier. 26 megabytes, approximately. 26.46 megabytes. That is, if I save this audio on my computer, it needs a file of 26.46 megabytes if we save it in the raw form without any compression. To confirm, I have saved it. In fact, so this is a file I saved as a WAV file. It's actually 27 megabytes. So it was slightly more than 300 seconds. So this is illustrating how we convert our input analog data or signal into digital data, which is the step that we needed here. Had analog coming into my laptop, it converted from analog to digital, and then I can send that digital data across the Ethernet or across my wireless LAN and can be received by other computers and played back. We have 10 minutes remaining. Any questions so far? That's about how do we send analog data as digital signals? Well, we convert that analog data into digital data and then send the digital data however we like as digital signals using Manchester encoding, using any encoding. And the basics: sample the analog, map each sample into one of the code numbers, one of the levels, convert that to a binary value, and we have our digital data. Increase the sampling rate or increase the number of code levels, will increase the accuracy at the receiver, because the receiver receives the digital data and reproduces the analog data. Increasing these two values increases the accuracy of the reproduction, the quality, but it increases the number of bits that we need to send or to save. I saved my file with 26 megabytes in size. If I used a higher sampling rate, it would be a larger file, use up more space. If I wanted to send it to someone with a higher sampling rate, I'd have better quality, but I'd need a larger file and need to send more. That's the trade-offs. There are ways to improve upon PCM. You can look at that in your own time. There's alternatives. Delta modulation is another type of modulation, similar, but uses the differences between the input signal. There's an example of that there. But that's all we wanted to cover for this analog to digital conversion. PCM is the primary example. There are others, of course. In the last 10 minutes, we want to finish with what happens if we want to transmit analog data as analog signals, which is coming back to my wireless microphone, my wireless transmitter and the microphone. That is, the microphone had analog signals, and the input was analog data, the voice. I want to transmit that analog data as an analog signal between the microphone and the wireless transmitter, and between the wireless transmitter and the wireless receiver. How can we do that? A common thing we do is we modulate the signals. We take the input, say my voice, and we use a carrier frequency, another signal at a different frequency, FC, to produce the output signal that we're going to transmit. And that output signal has a bandwidth centered about the carrier frequency. Why do we do this? Why do we transmit at a different frequency? There are different reasons. Sometimes if we want to convert the digital data, we must convert it into an analog form. Often we need to transmit at different frequencies to achieve the characteristics that we want. With my wireless transmitter, it uses a frequency of around 670 megahertz, because that's what's allocated for wireless microphones, and that frequency will not interfere with other transmissions like my laptop, and it's a frequency to cover the approximate distance needed of several meters between the transmitter and receiver. How do we do this conversion? We're dealing with analog signals again. We can change the amplitude, the frequency, or the phase. And we get what's called amplitude modulation, AM, frequency modulation, and phase modulation. AM radio, FM radio use these techniques. The next slide. This slide illustrates amplitude modulation. This is our input data. A very simple view of some data, just a sine wave. If we're returning to our example, if we had the plot of my voice here, that would be the input data. The plot that I showed you on the screen of it going up and down, then some silence, and up and down, and so on. This is our carrier signal. It's simply a sinusoid at a particular frequency, the carrier frequency. And this is the output signal that we transmit. This is generated from combining these two, in that we take our carrier signal, and with amplitude modulation, we change the amplitude of the carrier as the amplitude of the input data changes. When we've got a high value here, we've got a high amplitude of our carrier, And the low value, we've got a low amplitude of our carrier. So you can see the shape here, the amplitude of the carrier matches the amplitude of the input data. That's amplitude modulation. So the input data, the carrier signal, the output signal. And the other two are similar. Phase modulation and frequency modulation. Here's our input data, our carrier. The carrier has a particular frequency. With frequency modulation, we change that frequency. When the input amplitude is high, we increase the frequency of our carrier. When it's low, sorry, the other way around. When it's high, we decrease the frequency. We see we have a low frequency. When it's low here, we increase the frequency. We've got a high frequency here. And this is what FM radio does. This would be the input audio, the music or the voice. We'd have a carrier frequency. If your FM radio was using the channel 105.0 megahertz, that's the carrier frequency. And we change that frequency based upon the input. And that's what my wireless transmitter is doing. The carrier frequency is around 670 megahertz. As my voice changes, that frequency changes. As my voice amplitude is high, it changes the frequency of the carrier, and as it's low, it changes the frequency in the opposite direction. And this is what would be transmitted by my wireless transmitter to the receiver. So we've covered all four cases now. Analog data, voice transmitted as an analog signal using modulation, frequency modulation, phase or amplitude modulation. Converting the analog to digital at my laptop. We have an input analog coming into my laptop. It's converted to bits. We can send that digital data as either digital signals across our wired LAN using some encoding scheme such as Manchester encoding, or we could send it across wireless LAN using analog signals, the digital data as analog signals, using, for example, phase shift keying and amplitude shift keying. And that's our four cases covered. So we're going to finish there on this topic, and next week, our last lectures before the exam, we're going to move on to the one last topic. So here, of those four cases, make sure you can distinguish between them. Don't get confused between frequency modulation and frequency shift keying. One is for digital data as analog signals. This is for analog data as analog signals. So whenever we're transmitting analog signals, we either change the amplitude, phase or frequency. But there's shift keying and modulation. Understand how sampling works. The trade-offs between the sample rate and the code numbers, the number of levels. And understand how you'd interpret the different encoding schemes, such as Manchester encoding, converting digital data to digital signals. That finishes this topic and finishes for this week.